All right, everyone. Well, welcome to week 6. We are in the height of midterm season, as I am sure you all know. Let's go ahead and get started with a few announcements. So we have a Pacific Life info session coming up, and Pacific Life, if you don't know already, is an insurance company based down in Newport Beach, California, and they are coming. We are having an info session with them over Zoom on November 18th from 4 to 5 p.m. There will be more information sent out on that as we get closer to the date, but this is a good opportunity to talk with recruiters. So I definitely recommend that you spruce up your resume before then and come check it out. So the project showcase, which happens in spring quarter every year, is officially scheduled for April 14th in the morning. So if at some point this year you do decide that you want to do a project, this is where you will have a chance to present to the club with other teams that are currently working on projects. And after this event, there will be a networking session with different employers as well. So there will be more information about that coming out later, but stay tuned for that. If you are a part of the Big Little program, make sure to send your family names by the end of today. So preferably the end by the end of this meeting, but today is fine too. And for the mentorship tip of the week, what is a good minor double major to take with stats and data science? So computer science is the obvious choice there, but if you're not looking to do something along those lines, you can pretty much do anything in the domain area that you want to study. So if you're interested in like psychology or something, you can take on those different subjects. You can study life sciences, you can study economics, you can do whatever. If you're interested in language, you can be like an English minor or something. It's really up to you. Data science really is applicable to just about any area. So what are some good skills and tools to learn on my own time? So R and Python are the two big ones. Obviously you're here because you have some familiarity with Python, but another one that might be of use to you is this program called SQL. If you've taken P-Stat 10, you might have seen this before because RStudio, you can run SQL in RStudio as well. And SQL is generally something you would want to use if you were to, say, like query a large data set or work with a lot of large data sets. So that's it for the announcements. We'll go ahead and jump into the lesson for this week. And today we'll be going over supervised machine learning. So if you remember from some of our earlier lessons, you'll know that the difference between a supervised machine learning project and something that's unsupervised is that our data set is labeled. And in terms of the pipeline, your order of operations is going to look something like this. You'll first start off with your raw data set that you're going to split into your training and test sections. You'll do all of your analysis and cleaning, which we've gone over in past weeks. And then once you've decided on a model and a method, you'll probably work with the model for a little bit, tune your hyperparameters to the right specifications, and then you'll validate. And you'll repeat the process essentially until you deem that your model is appropriate. Now for testing it on the test set, and we'll go over what partitioning the training and testing sets, what those mean in a few slides. So there are two main types of supervised learning, and the first of which we kind of went over last week with linear regression. Regression is essentially predicting continuous values. So if you have like a continuous variable, say like the price of a price of a product, or like housing prices in the real estate market, that would be considered a regression problem because the house of a price can effectively take on any value. So the other type would be classification, and that is a little different in that what we're predicting isn't exactly necessarily a continuous number or something like that. Rather, we're predicting a category that a piece of data belongs to. So if you'll remember the Titanic data set, we're predicting whether or not people survive or not. Alive and dead are two different categories that you can fall into, and that's why it's a classification problem. Similar would be something like an image classification project where you are given like an image or something, and your model has to come up with what the object in the picture is. All right, that's classification. So yeah, like I mentioned before, there are a few different kinds of common classification problems that you might see. Dealing with like handwriting and written language data is a very common classification data science project that you will see. Another one you might be familiar with is classifying whether or not an email is like considered spam or not, depending on the content. So in a project like that, you would like run like text data through your model, and depending on the content, you'd be able to classify whether that email is valid or not. Facial recognition is another big one because not in this case, you're not exactly classifying according to two different binary classifications, but you're rather classifying into as many classifications as you want. So if you recognize a face, it could be any number of faces, right? So on and so forth. Again, the point of this at the end of the day is that we're trying to develop relationships between different features of the data. So this is something that comes up a lot. You're probably familiar with it, but pretty much every model, which is essentially an algorithm, has the same purpose, which is to develop relationships, right? So keep that in mind as we're going through. So when I say model, a model is really just like a function. So last week with linear regression, our model was just a linear equation, essentially, where we can take inputs, like inputs of X values, for example, and the model will give us an output, a result vector, anything like that. The way we develop this model, however, is it has to be trained. It has to learn from something, right? And that's why our data is important, because our model, our equation, our function, whatever it is, has to get its parameters from some sort of data, right? And the model does change depending on the data we give it, which is why validating the data is important. So what we do typically, once we have our data set and want to try to get a model fit to it, is we would take the model and fit it on the training features. So for example, in the Titanic data set, our features being like different passenger characteristics, the class of the passenger, the age of the passenger, etc. Those are training features and training labels. The training label in this case is the result, the Y value whether you survive or not. And depending on our training set, we then get to validate our model using a process called cross-validation. And we'll go over exactly what that is in a second. But once you get to this step and you try it out, if you realize that your model is not satisfactory for predicting your validation set, you would repeat the process. You would keep developing your model until it's sufficient to pass all of your tests. And then you do a final test on your test data to see if your model really truly is effective at doing its predictions. There's an important concept to keep in mind when you're going through this process of creating a model, and that is overfitting. And overfitting is something that occurs when your model function, essentially, in this case, learns the relationships between your features in your training data set a little too well. And what I mean by that is it essentially fits overly well to the individual data points and starts to not really capture the general trends of the data very well. This is a visualization of what overfitting looks like, just so you have a better idea of what I mean by that. And obviously, in this case, we have this sort of like parabolic shape to our data. The X's are a training set, which is a partition of our data set that we've set aside to base our model off of. And the blue X's are our testing data, which is essentially another partition of our same data set that we're testing the model on. Right, and when we create this model, we do it with the goal to fit these blue points just as well as they do the training data that it's based off of. In the overfitting example, we see that our model does a really good job of capturing the trends of our testing data, which are the red X marks, but it pretty much misses the mark when it comes to predicting the blue values at pretty much every point, because it doesn't do a good enough job of capturing the general trend. The one on the left does a much better job, even if it's a more simple model. So it just goes to show that having a more complex model isn't always better necessarily. This is a concept that'll probably come up for you if you're doing further research into cross-validation and all that, but model hyperparameters are essentially like the outside features of a model that aren't necessarily learned during the process of training. And what that means is, like for linear regression, for example, our parameters that are internal to the model are coefficients, are thetas, right? Each of the weights or coefficients of all of our different polynomial values, those are internal to the model. They are dependent on the data that you give it, but hyperparameters are different because they're kind of set outside of that whole process. A couple of different examples of that are the train test ratio. So say I have a data set of like 1,000 different individual points, for example. I can choose to make our training set 60% of the data, right? And then set aside the other percentage for testing. And that's not something that the model necessarily deals with on its own. It's something that I, as the data scientist or the researcher, has to define beforehand. Similar concept with batch sizes. For neural networks, if you are familiar with that, the learning rate is another hyperparameter. It's not determined by the model itself. Same thing with model depth, model complexity, similar to here. The depth of the model, the complexity, we can control as well. As we'll see with decision trees, this is a common hyperparameter for decision trees. How many nodes we have is a hyperparameter. So k-fold cross-validation is essentially a specific kind of cross-validation where we split our training data and our test data into a certain k number of partitions and then cross-validate. So we have one complete data set. We take like a part of it, set it aside, that's our training data, take another part, set it aside, that's our test data. We don't touch the test data until we're ready to test our model. That we set aside, we don't alter it in any way. For k-fold cross-validation, we are essentially defining a k number of partitions for our test data to cross-validate on. So in this case, we have 5 different partitions. We split our training data into 5 equally sized groups. This would be considered 5-fold cross-validation because we're working with 5 folds or 5 parts. The training set is essentially k-1 parts. So in this case, 4 parts of the whole partition that we've done. And our validation set is the 5th part. All right, it's just 1 part out of the whole. And then we do that, k number of times. Each time a different part, different fold becomes our validation set. So you can think of it as sort of like a miniature version of train test splitting, where our training data is getting split. Except in this case, instead of calling the partition we're testing on the test set, we're just calling it validation. So we're doing that k number of times. I think a good analogy for this would be, say a professor takes like 100 test questions out of a bank for like their midterm or something, right? And he says, okay, I'm going to take 80 of these questions and give them to you as practice. The other 20 questions are going to be on the actual midterm that you have to take. And out of those 80 questions, you have to essentially like study, right? You take those questions and you study, you try to figure out what kinds of questions am I going to have on the midterm. And then based on your performance, you take like a mock test of those 80 questions, and whatever score you get on that, you can assume would be similar to what you would actually do when you take the actual test, the actual 20 question test, which is your, in this case, the testing set. So kind of similar with the model, it's learning off of a percentage of the data that you predefine. The end goal is hopefully the model performs just as well on the test part. Hopefully your model performs well on the actual midterm. So. At the end of doing all of your fold calculations, you'll end up with a k number of metrics. In this case, you could, for example, evaluate your model based on accuracy. You could also use error. And essentially the mean of these k number of metrics is your cross-validation metric or your score. So yeah, this is just a review of that. Train your model, validate, do some adjustment, and then you test. Again, since this is a parameter that you define as the researcher, as the data scientist, you can decide essentially how to split your data. There's no hard and fast rule on how to do this, but something like an 80-20 split is usually pretty acceptable in those situations. If you have fewer observations, you might want to work with a set that's a little more evenly distributed, like 60-40, something a little more even on both sides. If you have more data, you can work with something like 90-10, even 95-5. The most important part to consider is that your testing set has enough observations in it so that you can actually get like a reasonable estimate of how well your model is going to perform on it. I think a good rule of thumb is that your test set has at least like 100 observations, I would say. Metrics to look for, we went over mean squared error a little bit before. This is essentially just the difference between the point and the predicted. So each data point that you observe and like your line or your regression line, whatever that would be. For classification, your metrics are a little different just because they're discrete values. When you're tuning your model, you can pretty much pick from any metric you think is appropriate. You can use several metrics as well if you want higher accuracy. These are a few different ones. Essentially, what all of these abbreviations are like true positive for TP, false positive. You can produce like a confusion matrix or something if you want to visualize how well your model performs. And that's essentially like for confusion matrix, you want to have like the number of values that are predicted accurately is true. The number of observations that are accurately predicted to be false. This is for binary classification, and then under diagonals, you would have like two values which are both like the false positive and false negative, which means your model inaccurately designated certain data points as either positive or negative when their actual label is the opposite. So that's essentially what this is describing here. I wouldn't worry about that too much, but it's just something to keep in mind. This is more for your reference, but say, for example, if you have good metrics when you're cross-validating and training your model, you would probably take these different steps to fix the problems that you're having. Right, at the end of the day, if you end up with good metrics, your error is generally low and you've tuned your model to your validation set very well, you can move on to testing with that test set that we set aside in the beginning. And once we've done that, we've essentially arrived at our final model, and we don't do any more alteration to it, because by then we will have known whether or not it was appropriate or not for the data that we're using. These are just links for the documentation for a few different methods for regression. K-nearest neighbor is a common one for regression. I will post the slides. I think you already have them actually. And you can research a little bit on your own about these different methods. Random forests, I'll point out, are a bit like decision trees. The only difference is that it's a form of ensemble learning. And if you don't know what ensemble learning is, it's essentially using, instead of one model or estimator to test your data, you're using a bunch of different models. So in a random forest, you're creating like a bunch of different decision trees, and you're essentially using them all to predict. And you tend to get better predictions that way just because of using averages and whatnot. For classification, you can also, some of these models you'll also see in regression. That's just because they can be used for both. There are two different types of decision trees, and one can be used for regression, one can be used for classification. For classification, it's called decision tree classifier, and that's the other one is decision tree regressor. Again, you can look at the documentation for all of these things. I encourage you to do so because the documentation for all of these methods includes all of the parameters, right? Each of these is a hyperparameter that you can set, right? So if I wanted to regress with a certain depth for my decision tree, I would be able to set that when I run the function, right? And all that information is here, including like examples of how to use everything. So These are just a few different video references that I encourage you to look at after the lesson, if you have time, if you're interested in any of these different methods. Yeah, and these are the links for this week. That's pretty much it for my lesson, but I will go over a couple different points before you guys leave related to the notebook, one of which is opening the notebooks. I've been told that there's some issues with opening it, which I'm not surprised by, but if this helps you out at all, try opening the notebooks in Google Colab. You might have to add this as an extension in Google, and note that you can search this up in Google, the Google Marketplace, like you see here, but you have to search it spelled with one L. I know it's weird, but that's just how it is. And you should be able to open it if you have it as a connected app here. If that doesn't work, you can download the file on its own and run it in like Jupyter Hub. If you don't know what Jupyter Hub is, you've never used Jupyter, come talk to me so I can help you set that up. But I will post the link to the installation page for that in the Slack. Another point of note for the notebook, let me see if I can find it. There's one section on one hot encoding, and what that is essentially turning a categorical variable into something that a machine can read, so a number, right? And that's essentially what this is. If you want your model to be able to identify what these different colors are, you would encode them into numbers, either ones or zeros, right? So for each of these IDs, which are different like entries in your data, you would transform it to something that looks a little bit like this, where if it identifies correctly with the color red, which is in the first column, it would have a 1 next to it. If not, has a 0. This way, it's a little more machine readable. And that's essentially what this is referring to when you see one hot encoding. Okay. The other point I want to make is when you train a model, pretty much in any program, but in Python specifically, you're going to want to specify a random state. This is just a parameter that belongs to each of the classification and regression models. It's like a random number generator. It sets beforehand the randomization so that every time you include the same random state, you can reproduce the results you get, right? Every time you run like a model classifier or regressor, it can give you different results just because it learns differently depending on how it's initialized. This way you can keep it constant. But yeah, that's all I have for you this week. Thanks for coming out. If you have any questions, I will be here for like 10 or 15 minutes after here. But yeah, that's it. That's all I have for you guys.